Hey there. Hope everybody's doing well today. Today we're going to talk a little bit about topic 2 in chapter 5. So topic 2 in chapter 5, the gentleman who wrote this textbook, my very good friend Mr. Barry Edgar, he called it Stronger Eyes and Better Numbers. So when Mr. Edgar was talking about stronger eyes, what was he talking about? Well, right here, the telescope. So the telescope was his what allowed us to have better eyes, but also using the telescopes and a lot more accurate measurements and more data, we got better numbers in terms of some of the movement and some of the time periods that things take to move through space and time. So stronger eyes and better numbers. So when it comes to telescopes, it's a lot of controversy probably. If you look, who was it who invented the first telescope? It was accredited to several different people who were all kind of working around the same time period. But the first official patent was awarded to a man from Holland whose name was Hans Lippershey. And he was actually an eyeglass or a spectacle maker. And he didn't really make it originally for looking into space. He just made it for looking at distant objects and be able to see them clear. So the first telescope was invented by a Dutch spectacle eyeglass maker whose name was Hans Lippershey, right around 1608. A lot was going on at that time, however, with lenses, and there were, in the next few years, a lot of people developing their own telescopes. What allowed that at this time was the fact that the lenses they were able to grind were so much better. The technology developed for that so that they could be used for developing telescopes. He used two lenses, one in front of the other, to magnify distant objects. So he would have one over here closest to the object he was looking at, and one over here right next to his eyes. If you've ever used a magnifying glass and just held it up to look at a distant object, if you look at something close, it looks fine. Hold it up to look at something far away, and it goes upside down. That just deals with the refraction of the optics. You may have taken some optics in grade 8 science. I know when Mrs. Blake was teaching it, she would always sometimes even borrow some equipment from me and do some optics work. So telescopes, nice. One of the people who was often given credit for inventing the telescope was Galileo. So Galileo didn't invent the first telescope, but in about a year after it was invented, in about 1609, he built his first telescope. And he used it to study the stars. The thing about his telescope, it was a lot better. So shortly after Lippershey's invention, Galileo built his first telescope in 1609. Galileo was an Italian astronomer who improved the telescope and used it to study celestial objects. Remember that word, celestial objects, referred to things in the sky, natural things, not airplanes and meteor and satellites and space station and things like that. So here's Galileo looking out into space. Fascinating gentleman. He lived his home was actually in Pisa near Florence, and which of course is most famous for the Leaning Tower of Pisa. And if you ever get the opportunity to travel to Italy someday when COVID's not restricting our travel so much, absolutely do that. Florence is probably one of my favorite cities in the whole world. And Pisa is very interesting. It's a small walled city which basically has a great big church chapel, which is called the Duomo, in it. There's the main Duomo, there's the Baptismo, where they would have to baptize people before they were allowed into the main church. And then there's the bell tower. And the bell tower is leaning over, and that's the famous Leaning Tower of Pisa. A lot of interesting science and physics going on there. The acoustics in the Baptismo is amazing. And in the Duomo, the chapel, there's a lantern, lantern that hangs, it's a candle lantern, hangs from the sky, and they'd have to lower it down on a rope. And it's believed that watching those sway back and forth in the pendulum motion was what Galileo used to develop his whole law of pendulum motion and allowed first clocks to actually be invented. Before that, the only timepieces were either sundials or sand clocks. So Galileo Galilei, Some of the things that he looked at was the moon, and he made some really interesting sketches of the moon. So Galileo observed the moon's blemishes, which were the shadows that lengthened and shortened when the sun's angle on them. Galileo concluded that the moon's surface has mountains and craters on it, much the same as the Earth. So as the shadows moved, he realized that there was revolution of the moon going around and the sun reflecting off of it. He also observed the sun quite carefully, which is not a good idea to be looking at the sun with your bare eye or with a telescope, but it had spots on it. Over a period of a month, the spots moved across the surface, disappeared, and reappeared again on the other edge. From this, Galileo concluded the sun actually spun around, rotated on its own axis. He also observed so this is Jupiter. He observed the 4 moons, or he observed 4 of the moons of Jupiter. There's only 3 that you can see here. Again, the reason we see Jupiter, it looks like it's shining light at us. It's not, it's just reflecting the sunlight. The reason we see these moons here is, again, because they're just reflecting the sunlight. The only thing which radiates its own light is a star. And of course, our sun is an example of a star. So Galileo observed that Jupiter is accompanied by 4 small moons that move back and forth across it. He concluded that Jupiter is orbited by moons, and he could tell by their motion that they would disappear as they went around and around and around. It started to show again that, hey, here's one of the planets. It's got some moons going around it. Maybe, just maybe, if you look at the work of Copernicus, and his idea of that heliocentric model, that the sun was the center of the universe and all of the planets, including Earth, go around it, started to make a lot more sense. When viewing celestial bodies through his telescope, Galileo observed that the planets were disc-shaped. He saw that the planets in some detail. However, the stars were still pinpoint way far in the distance. He could not see the stars with more detail by using his telescope. This observation led Galileo to the conclusion that the stars were much farther away than the planets. So Galileo started to publish a lot of his scientific results, and Galileo decided that yes, Copernicus was correct, and the old Aristotle model of the geocentric, the Earth-centric model really wasn't right. Galileo got into a lot of trouble because back then the church was equally powerful in terms of the law as the government itself was. Italy at the time wasn't a single country. It was a series of a bunch of different principalities, and so back at this time, he got into trouble. So they told him to quit preaching his science and stay to the church doctrine. Because he was very famous and very popular, they didn't just go out and arrest him and execute him. However, after quite a long time, he did calm down a little bit of his ranting and his raving about it, but he did still publish a lot of scientific paper where he at least implied that the heliocentric model was correct. He got called in front of the Grand Inquisitor, and he got sentenced to house arrest for the rest of his life. So you can see this is a famous painting of him, and it's got beside it that we can't see on here the words inscribed, and yet it moves, because the Inquisitor had said to him, you must accept that the Earth is the center of the universe, and the planets and the sun revolve around us. And his response was, and yet it moves. Using his telescope, Galileo spotted 4 moons orbiting Jupiter. Apparently, not everything revolved around the Earth after all. With modern telescopes, scientists have now found that Jupiter actually has 17 moons, and some of them are quite large. So here's a famous painting again of Galileo. He was much older at this time, and he looks there facing the Grand Inquisitor. He lived from 1564 to 1642. He He's sometimes referred to as the polymath of Pisa. The polymath. So one of the things we're going to do in this class over the next couple of months, if everybody just looks over to the side bulletin board on your left. So on your left, we have our word wall, and that's last year's word wall. It's up there actually right now. But the very first word up in the upper left-hand corner is etymology. And etymology is the study of word structure. And that's really important in science because quite often you will see a new word you hadn't seen before, but by being able to put the parts together, you can figure out what that word means and what it refers to, because we use a lot of the same prefixes and suffixes in our science classes. And actually you can see the word a little further way over on the right-hand side down towards the bottom. On the right-hand side, polymath and autodidactic. Or autodidact. Polymath, if you look at the beginning, poly, it means many. And many, in this case, math, doesn't refer just to mathematics. It actually refers to subjects. So a polymath is a person who is very knowledgeable, very well educated, very intelligent in many different areas, subject matter, so many different sciences. So in the case of Galileo, he understood physics very well. He understood math very well. He understood biology very well. He understood, not unfortunately social studies so well. He got himself into a lot of political trouble, but the polymath of Pisa because he was from Pisa. And that, of course, speaking of words that are going to be important to you, is alliteration. Alliteration. So what is alliteration? It's when you have several words that start with the same letter or the same sound in some cases, but polymath of Pisa, as in shakes so my single state of man that function is smothered in surmise. Okay, the word beside that, autodidact, means auto, self, didact, learning is a self-learner, and a lot of Galileo studies were again where though he was very well educated in a formal stance, he did a lot of self-learning as well. So very impressive gentleman. But in 1833, he faced the inquisitor from the Royal Catholic Church and was found guilty of heresy. He spent the rest of his life under house arrest, and in fact, he became quite ill shortly before his death in 1642, and actually went totally blind. And they wanted to take him out for treatment, but he was not allowed to leave, and so there was some appeals made on his behalf, but didn't quite work out. Interesting gentleman. I do have an article, so if you do finish your work anytime this week, and we're going to have some literacy time coming up, so keep that article on Galileo Galilei, it's a Wikipedia article, in your red folders, and bring it to class each day just in case. Excellent, thank you. So what are the parts of a basic telescope, going back to Galileo's telescope or Lippershey's telescope? Basically, they're made up of the following pieces. So two lenses with a tube around it. So the one lens which is closest to the object is called the objective lens. So the objective lens is close to the object. That's easy to remember. The part which is closest to your eye is sometimes referred to an eyepiece, but it's also called the ocular lens. And ocular refers to eye. So that word, again, in science generally is going to mean reference to the eye. So the ocular lens or the eyepiece is closest to your eye. Now this is what we call a refracting telescope. So refraction, again, when you studied some optics last year, you learned about refraction. Refraction is the bending of light because it changes medium. So when the light travels, here's where it would be traveling normally. When it enters that more dense medium, it bends. And it's going to bend towards something. When it enters, it bends one way. When it exits, it bends the opposite way. But the ultimate result is it's bending inwards. So it's sometimes this would be called a convex lens, or it's going to be called also called a converging lens because it converges the light together and focuses on a focal point. So because it only has lenses to help magnify, only has lenses to help magnify. It's called a refracting telescope. So when we talk about the resolving power of a telescope, the resolving power is not going to help you focus or zoom in closer. Greater resolving power doesn't mean you can zoom in closer. It means you can just get a clearer image with better detail. So here's an unresolved with poor resolution, low resolving power. If you double the D, and the D we're going to see is diameter in a second of the lens, it's barely resolved. If you multiply the diameter by 4, it gets fully resolved. So this is what you're actually looking at with that telescope. This is the way it looks at with just a not very thick, not very high diameter telescope. So we're talking about the thickness of the lens. How do you zoom in farther? Well, it deals with lenses farther from each other and stuff. But by increasing the diameter, get a thicker lens, what it's going to do for you is make you see the detail a lot better. It doesn't zoom it in, it just makes it higher detail. So that's what D stands for, is the diameter of the telescope. So generally speaking, the larger the diameter of the lens, the more resolving power of the telescope, the better you can see fine detail. So here's a nice picture of, again, you can see that this telescope is going to have very, very big diameter. So that each of the lenses in there, so you can see compared to some of the pictures of the ones that Galileo had, much bigger diameter. So you can't zoom in any closer, but boy, you're going to see much finer detail. So if Galileo's telescope was about the same length of the tube, he might be able to see some structures on the moon. But with this telescope, you can see them much closer. A lot of people have binoculars at home, or perhaps your parents have a telescope for hunting and for finding different animals that they might be looking up in the mountains on the slopes and everything. So you'll see this one has a much bigger diameter, so good resolving power on this. So again, we're going to look at 3 types of telescopes: revolving, reflecting, and refracting telescopes. So the first, again, is that refracting telescope that we've seen already, only uses lenses. So they've got the objective lens and the ocular lens, the eyepiece. Sometimes the magnification is only done by mirrors. So you can see it comes into a curved mirror, hits a secondary mirror. That's what does the magnification. So that's referred to as a reflecting telescope. So even though it's only using mirrors to magnify, it does still use a lens to help us just to focus that image. So it does use a lens. All telescopes use a lens, whether they're refracting or reflecting. But in a reflecting, the lenses don't magnify. The third type, however, is called a combination telescope, and it uses both lenses and mirrors to help to magnify. So that's a combination telescope. So there was a very interesting gentleman whose name was Johannes Kepler, and at some point in the near future, we're going to watch perhaps a video on him. But I don't think we're going to plan to do that in my absence. We'll wait till I'm back. So let me tell you a little bit about Johannes Kepler. Johannes Kepler was born into a family where his father was a mercenary. He was a soldier of fortune, and he didn't stick around very long. After Johannes was born, he was gone shortly after that and never did return. It's not clear whether he died in a far-off war somewhere or if he just chose not to come back. His mother was very intelligent, very, very smart lady, and I think Kepler probably inherited a lot of his intelligence from his mom. So what was it that you did with women back then if they were really smart? Well, you called them a witch and they burned them. So Johannes Kepler's mother was actually burned as a witch, and which politically put him not into the greatest of situations as well. But he was very intelligent, managed to get into school, get into university, and was very well educated. Johannes Kepler lived about the same time as Lavoisier and Galileo, from 1571 to 1630. And again, Kepler was a brilliant mathematician and a polymath again, very intelligent in many, many areas. And he was able to do some amazing things, which we're going to see a little bit. So his interesting family history, again, was about his mother and father. And though he got a fair amount of respect as a scientist, never really made a fortune doing it. He probably made more money doing people's horoscopes than he did actually doing his science work as time went by, because he would do horoscopes for rich people for fun. So there was another, going back here for a second, he was able to acquire the data of Tycho Brahe. Now, Tycho Brahe is the way that I pronounce his name. You're going to find it pronounced in many, many different ways in different movies and different videos and different professors. I've heard Tycho Brahe. I've heard Tycho Brahe. I just say Tycho Brahe, and you can pronounce his name any way you want. Tycho Brahe was a very interesting character as well, and he was from he was from Denmark. And Tycho Brahe was a very, very wealthy Danish astronomer. And one of the things, he was very, very religious. One of the things he did was he hired several people to observe the motion of the planets and the stars and write out the descriptions of the planetary motion. Kept very, very careful detail and times for the amount of time it took for planets to revolve and everything else. So 1546 to 1601, a wealthy Danish astronomer built an observatory and hired many people to observe and write out descriptions of planetary motion without the use of telescopes. So again, this is before the use of telescopes. The amount, because he hired lots of young scientists, very, very good information. What his intention was to take the information, the data he was acquiring, and to use it to prove the church's position that the Earth was the center of the universe and all the planets went around us. As he was getting ill, he decided, he had heard of Kepler, he called on Kepler and he said, I'm going to leave you, I'm going to will this to you, all of this data. But what happened was, Brahe's family, when he died, they knew that Kepler was going to use that in other ways. They knew that his feelings, so they refused to give it to him. So Kepler ended up breaking into Tycho Brahe's family house and steal all this information, all this data, these scrolls and scrolls of information with all the planetary motion on it. Kepler used Tycho Brahe's data to determine that, first of all, the planets do indeed orbit the sun. There were some really interesting things going on. If you actually watch Mars go through the sky, it goes for a while, it seems to stop, do a stutter step, go the opposite direction for just a short period of time, and then return in its way going around. So if that was Mars revolving around us, that would make no sense at all. So some of the people before who still had that geocentric idea, they talked about epicycles. So they said, no, the planets do go around the sun, but then the sun goes around us. We're still the center of the universe. So that was one of the ways to try and, as more and more of this data was coming out, and again, we'll talk a little more about this later, but the planets do orbit the sun. The data was completely undisputable. That was the fact going on. But the math didn't quite work out. When he plotted out the motion, you had the sun at the center of the universe and the planets going around in a circle. The motion didn't work out quite right. And that's because we don't go around the sun in a circle. We actually orbit the sun in an elliptical shape, not a circular orbit. So what is an ellipse? An ellipse is kind of an elongated circle. It's like a circle you push down and crushed, kind of watermelon shape. And in a normal circle, you have the center point, and you have the circle equal distance from that all the time. What an ellipse has instead is two epicenters, or two focal points. So the sun is one of our focal points, one of our foci, and then there's just a place out in space which is the other. And so the Earth goes around the sun, and the planets go around the sun in a slightly elliptical manner. That's now known as Kepler's first law of planetary motion, where you've got the Earth going around the sun in an ellipse, and the sun is one of the two focal points, and the other focal point is just a place out in space. Now, before we go to Newton, let me just finish this off then. It's very interesting because as it turns out, you think, oh, well, maybe that makes sense. Maybe during summer we're close to the sun out in this area, and then in winter we're farther from the sun. As much sense as that makes, it's wrong. We're actually at a point right now where we're on our way towards being closer to the sun. And when we get to this point right here, that's going to be our very, very shortest day of the year in December. And out here, when we had our longest day back in June, that's when we're getting into summer, when we're farthest away from the sun. So what affects our weather, our seasons, is not how close we are to the sun or how far we are from the sun. It's the tilt of the Earth. And I'll try and demonstrate that with a basketball when I'm back next week. So again, over here, when we are close to the sun in winter, that's when the southern hemisphere, South Africa and Australia, places like that, are going to be having their hot, hot summer. Because at that point, we're tilted, the north is tilted away from the sun, so the rays come and they're indirect. Whereas in the southern hemisphere, they get direct rays. But we'll talk more about that. So, not that many years ago, I took an engineering physics class from the University of Colorado. And my physics professor there was brilliant, but he always referred to Isaac Newton as the smartest man who ever lived. And a lot of people are going to say, well, Isaac Newton, shouldn't that be Albert Einstein? And you can make a good argument both ways. There's some differences, though. Number one, Einstein had several other physicists he got to work with, and he got to work several hundred years after Newton and have all of Newton's work to work on. So Newton was absolutely brilliant, super, super intelligent, invented physics, invented universal law of gravitation and the three laws of motion. And so much of what we understand now in terms of kinematics and dynamics and physics, it all goes back to Isaac Newton. So again, a brilliant, brilliant person and a bit of a rock star, especially if you look at his fancy haircut. All right. So back when I was teaching in the 80s, when heavy metal was really big, the students got a kick out of his haircut. So in 1687, Newton published the universal law of gravitation. And interestingly enough, when he developed his universal law of gravitation and he developed his three laws of motion and he invented calculus, something was going on in England at the time. Isaac Newton at the time was teaching at Oxford and Cambridge, one of the most prestigious schools, and when I got a chance to visit there a few years ago, that was one of the things I was amazed at. When you walk around, you go, my goodness, this is where Isaac Newton used to walk back in the 1600s. It's just phenomenal. But the bubonic plague had, speaking of pandemics, had hit England, and people in London were dying like crazy. So much like we did last spring where everybody went home from school, they did the same thing, and they actually went for a few years. So Newton went home to the country and lived on his parents' farm in their orchards. And it was his time there where he had no teaching or preparation to do. He sat back and had a chance to actually collect a lot of his ideas and develop some of his famous laws, and actually invented the mathematics subject area of calculus. So there's the old rumor that Newton discovered gravity when an apple hit him on the head. Well, that's not exactly accurate, but yes, he was in his family's apple orchard area and thought about apples falling from the tree. So that's where that kind of urban rumor kind of comes from. So what does it say about the universal law of gravitation? It says, first of all, that there is a force of gravitational attraction between every object in the universe. So if you take any two objects in the universe, if you take the moon and you take the pencil that might be sitting in your hand, there is a force of attraction between the two. So why doesn't the pencil fall towards the moon? Well, it would if the Earth and everything else wasn't here. But of course, the gravity of the Earth, because we're closer, is much stronger. So there is that force of attraction between every two objects in the universe, and how strong that force is depends on the mass of each object and the distance they are apart. There, I corrected that very quickly. How strong that force is depends on the mass of each object and how far they are apart. The larger the masses are, the greater the force of attraction. But how far they are apart is the less the force of attraction. So you could take two very large objects with large masses, but if they're very far apart from each other, they will have less of a force of gravity pulling them towards each other than masses that are smaller, but they're closer together. The distance is actually what we call an inverse square. So if you, in terms of masses, if you double the mass of one of the objects, you double the mass of, or double the force of attraction. But if you double the distance they're apart, you cut the force down to 1/4, 2 squared. If you 10 times more the mass, it's a 10 times stronger the force. If you 10 times the distance, it's 100, 10 squared, 100 times less of a force. So there's some interesting relationships there. It's a common theme in sciences that you'll start to learn a little bit next year, but mostly in Physics 20. So Isaac Newton. So think about what that means, because why is it that the planets are actually going around the sun? Why do they do that? Why don't they just take off out into space somewhere? Well, the reason is because the force of gravity, which is pulling the planets towards the sun. Okay, well, if that's the case, why don't we just fall into the sun? If we have a gravitational force pulling us, well, because we have that momentum, we have that motion. We're not stationary in space, and the sun's not stationary in space. We're actually traveling through space at thousands of kilometers an hour. We're going very, very fast through space. When they talk about that Big Bang theory, sometimes what that refers to, again, is that there was a massive explosion that sent all of the objects in the universe barreling through space, and the stuff in our area, in our solar system, in our galaxy, is all moving together away from other galaxies and other planets and other suns way across at the other part. And we're going to see that later on in this unit, where we get to look a little bit at some evidence for an ever-expanding universe. I just looked down at the timer. Holy cow, we're up to 32 minutes already. This was much longer than I meant to be. So Isaac Newton helped to explain with that force of gravity why it is we move in the way we do. Understanding gravity can now explain why the planet stayed in orbit around the sun. That's the end of this one. Sorry, folks, that was way longer than I meant to. That should help you get through some of your assignments, though. Take care and stay well.